a weapon. It's a tool. But Nina just brought it to my attention, so she would like to say a few words about it.
So yeah, I just wanted to say that, you know, every year we wait for to get our attention that the group is ready to start. But at the end of the last semester, Lars Hernquist thought it would be very important and a great idea to formalize Avi bringing to attention the group. So we decided to get him a gavel so that, that we would all be able to be ready for the start of it.
Thank you, Nina.
So test it out one more time. Maybe.
It's just a different source of sound waves.
Now we're ready.
And we can legislate this as well. So welcome everyone for the first ITC lunch of the fall semester. Just wanted to make a few announcements before we start. I first wanted to thank Eric Kito, our senior member, for his generous donation that supports the 2018-19 lunch series. So we are all grateful. And I should say this donation goes beyond, in addition to the generous donation that he provided for the Kito Prize that is given to the best PhD in theoretical astrophysics every year. And I would also like to welcome the new postdocs of the ITC. So let me call them one by one. Shmuel Bialy came from Tel Aviv University. Paul Duffel from UC Berkeley, before that NYU, so he's used to this weather. Razia Emami, over there, she came from the Institute for Research in Fundamental Sciences, but originally from Iran. And Rainer Weinberger, is he here?
Eastern Conference Institute.
Okay, he's coming from Heidelberg. He's not here today. As well as Anna Ijas, she's not here today. She comes from Columbia University. She's coming as a research fellow supported by the Simons Foundation. And Benedict Dimmer received the Einstein Fellowship. He was a postdoc at the ITC before that. And Erika Nelson is joining us as an Einstein Fellow. I don't know if Erika is here. So there, yeah. So we are delighted to have all of you here with us. Two other things. There will be a group photo taken next Thursday, unless the weather would not look good. We do not, as a theory institute, we know the pitfalls of numerical simulation, so we don't trust the weather forecast. But if there will be rain, then it will be the week after, the 20th of September.
Please try not to wear bright colored shirts because it really just flushes out in the picture, and don't wear horizontal stripes. Yes,
I should also mention the Black Hole Initiative events are starting next Tuesday with a talk. We have lunch at 1 p.m. and then 1:30 to 2:30, usually 2 talks. Everyone is welcome. It looks like the regional funding will last for 1 more year, but we are hopeful that we will continue with this center, that it will be funded beyond that period of time, and we have a path forward to follow that. So you're all welcome to join us on Tuesday there. And finally, last year several people brought to my attention the fact that there are some participants every now and then that decide to come in and have a sandwich, and then once they finish the sandwich they leave the room. And that's disrespectful to the speakers that speak afterwards. Not to speak about the speakers while they're eating, it means that they're not really here for the science, more for just the sandwich. And we would like to ask anyone that joins the ITC lunch to respect all the speakers and stay till the end. The good aspect of the ITC lunch is if you're not particularly interested in one subject, the good news is that it will last at most 15 minutes, and then you will move on to something else. So you're all welcome to stay here. So today we have 4 presentations. The first one is by John Forbes. He will talk about brown dwarfs more massive than the hydrogen burning limit. And then we move on to hear from Doug Lin, who gave the ITC colloquium just before lunch today, and that was a very insightful talk. We learned a lot of original ideas about AGN from Doug, and you always learn something new when listening. And so he will be here on sabbatical, and I encourage everyone to speak with him while he is at the ITC. He will speak in a few minutes about the dynamical evolution of the inner solar system during its formative years. And then we'll hear from Sean Andrews from the CFA, that will also give the CFA colloquium today. And he will talk about protoplanetary disk demographics. And finally, we'll hear from Sandro Tacella, who is a postdoc at the CFA, and he will tell us, he's sitting over there, will tell us about quantitative evaluation of gender bias in astronomical publications from citation counts. And in this context, I should mention that once a month we will hear a talk about equity and diversity, which are very important elements of our profession, and we feel that they are so important that we need to revisit them once a month. And we will also, another aspect of the ITC lunch this year is that we will also hear from students once every couple of weeks or every week, depending on the schedule. John.
Okay. Thanks, Avi, and thank you all for being here, and thanks to all the organizers who make this event happen. So today I want to tell you about some work I've done with Avi, how to make brown dwarfs more massive than the hydrogen burning limit. So let me explain a little bit about what I mean here. So when someone defines a brown dwarf, they almost always in the same sentence mention the mass. They say they're things that are less massive than stars. They're not massive enough to burn hydrogen. And that cutoff is about 0.08, 0.07 solar masses, and that's what we call the hydrogen burning limit. And basically the take-home message that I have for you is that there's a way you can get around that and get brown dwarfs that are actually more massive than that cutoff. So study of brown dwarfs actually started with theory, computation and theory, which is appropriate given the venue. So this paper in 1962 where he looked at a series of models of stellar structure and evolution, and found that some of them, they never got hot enough to actually burn hydrogen. So there's a fundamental lower limit to the mass of a star. And this is an incredible prediction because it took 33 years for them to actually find one of these. So anyway, people who study the sort of boundary between brown dwarfs and stars often take an approach that's actually very similar to this original approach, which is you take a series of models in the mass range around the hydrogen burning limit, and when you change something, you may change where exactly that limit is. But I think it's also very useful and a complementary approach to have an analytic model that helps you understand where this boundary comes from. So people have done this. So we're going to follow this classic paper in 1993, and there's sort of an updated, modernized, slightly version recently. And basically, the way this model works is that you start by assuming, well, we're only going to talk about very low mass stars, so they're going to be basically fully convective. So that means their entropy profiles are going to be flat. And this is a very well-founded assumption, but it's also very powerful because it gives you sort of for free the whole density and temperature structure of the star. And so that lets you write down, say, the radius, the central density, the central temperature, purely as a function of this, the normalization of the entropy profile and the mass, so just those two parameters. So in addition to that assumption, then you write down the relevant nuclear reactions. You have to account for the fact that there's a sort of a phase transition between the ionized interior and the molecular photosphere. So that actually introduces a little bump in your entropy profile. And so what you assume about that matters. And then you also finally need some opacity or opacity law at the surface of the star. And once you have those things, you can write down, usually just in closed form, an expression for the nuclear luminosity and the surface luminosity as a function of the entropy and the mass. And finally, the way the model works is if you want to have a star, you have to set these two things equal. So very, very simple. So what happens when you apply that condition? So we can look in this space of mass versus entropy or degeneracy. Well, this is 1 over degeneracy. They're proportional to each other in the interior of the star. And this curve is where the nuclear luminosity equals the surface luminosity. And you can see there's a well-defined minimum here. And so you identify that as the hydrogen burning limit. You say, this is the lowest mass a star could possibly be at some fixed composition. So maybe you're worried about some of the assumptions that went into this analytic model. So this is something we should check with real numerical simulations. So what I'm showing here is a series of MESA runs. So I have a bunch of different masses. And I'm plotting the isochrones, so where these models are at a fixed age. And you can see that they all start on the right-hand side of this diagram, not very degenerate, nice and hot. And then they all cool down. Ones below 0.07 solar masses or so just keep cooling. Ones above 0.07 solar masses eventually pile up on this sort of parabola-like line, very much in line with what we expect from the analytic model. Even though the analytic model doesn't quite, get it right in detail. They disagree a little in where exactly the minimum is, what the actual minimum mass is, but it's the right qualitative picture. So this is all well and good, so I wanted to think a little bit more deeply about this model because there's if you think about it, there's actually kind of a funny feature here. We saw in the previous slide that things on this part of the parabola are the main sequence of low mass stars. But what is this branch over here? Is there like another main sequence? Like what's going on with this left-hand branch here? Because if you think about it, this line is supposedly where you have things that can stably burn hydrogen, that should be stars. So I was really intrigued by this like second branch of models, and I tried really hard with MESA to produce something that sort of fell in this line. So I took sort of the standard models that I showed you earlier that have tracks that look like this, and I just added mass to them. I didn't know exactly where this line was, so I had to try a lot of things. I also tried just freezing the stars, cooling them down artificially. And nothing worked. You could never get a model that actually lived on this line. And the reason is, if you think about what this line means, on one side of the line you have that this line, remember, is nuclear luminosity equals surface luminosity. On one side of that line, that means you have the nuclear luminosity is greater than the surface luminosity, and on one you have nuclear luminosity is less than the surface luminosity. When this is the case, you get sort of brown dwarf behavior. You're losing more energy than you're producing, so you just cool and cool and cool forever, unless you run into this main sequence line. In this region, it's sort of like a nuclear meltdown. You have a lot of nuclear energy that you can't get rid of. You can't get rid of that energy, so you heat up the interior and you move to the right. So what that means is that actually in sort of a perturbative sense, this line is stable and this line is not. So that's why you don't get anything over here. But so I mean that's a little disappointing. But a corollary of that is that you can divide this space up into 3 different regions. So this region to the left of this line here, you have stuff that's more massive than the hydrogen burning limit, but that behaves like a brown dwarf. It's not burning hydrogen, and it's just cooling forever. So you can sort of divide this space up into ordinary brown dwarfs, stars that are on the path to the main sequence, and brown dwarfs that are more massive than the hydrogen burning limit. And you can look at what these models actually look like in more observational space. So this is the mass radius relation. These yellow, green, purple lines are models that are just sort of vanilla evolutionary models where I haven't done anything strange. And you can see that the brown dwarfs are just cooling and contracting. The main sequence stars are expanding over time, just like you expect. But if you take these models where I've added mass and they've ended up in this region over here, they fall down here in this right-hand corner where nothing was before. And so they're basically just a continuation of the brown dwarf sequence, and this is true in other observables as well. And they behave just like brown dwarfs, they're just a little more massive. So now the question is, how do you actually produce these things? It's very difficult to sort of flash freeze a star. If you have any ideas on that, let me know. But I think obviously the more plausible thing to do is to take a brown dwarf, wait until it's cooled past sort of the lower end of this minimum, and then add mass to it. But you have to add mass slowly because when you add mass, you heat it up, and if you just dump a ton of mass on a brown dwarf, then naively in this diagram you shoot way to the right, and you end up igniting the brown dwarf, which is now a star. So you have to add it very slowly. So we've thought through a few candidates and discarded most of them. I think the only really plausible way to do this is to have a stable binary mass transfer. But you need sort of special circumstances for that to happen, but these aren't implausible. So in the end, the takeaway is that you can get hydrogen-rich objects that are more massive than the classic boundary between stars and brown dwarfs, but they're not burning hydrogen. These are just brown dwarfs that are a little more massive. And they're probably a small minority of brown dwarfs, but there should be plenty of them in the galaxy. And for more, you can see our paper on the archive, and I'm also giving a longer talk at Avi's group meeting next Friday. So, thanks.
Sure. So on the last slide, you mentioned if you have stable mass transfer, you can keep growing this thing as long as you transfer mass slowly enough. So did you calculate a kind of an upper mass, but is over massive brown dwarf?
Yeah, so it's a little unclear exactly how slowly you need to add the mass, but order of magnitude, you can get up to 0.1 solar masses. So you can sort of increase their mass by 50%, plausibly. Yeah, I think that's very clearly the right thing to do, but I haven't done it yet.
So you said it's a problem to get to the other branch because you always start at the right corner and then you cool off. So what determines the starting point? Why can you start the formation maybe from the molecular cloud phase at the cooler?
Well, so I mean, if you think about this parameter here, this is 1 over the degeneracy of the gas. So things that are over here have sort of 10 times as much, well, 1/10 the thermal energy as the electron energy. So they're very degenerate. So it's tough to imagine a scenario in a molecular cloud where you get something like that. But if you have some exotic scenario.
Switch to sound ports. Where do I put this in? Huh? Okay. No, it doesn't work. Oh, yeah, right. Right. Okay. Right. Okay, for today I'm just going to talk about a project that, one of the projects I'm doing. Something that most people know something about, that asteroids, there's minor planets between Mars and Jupiter. They tell us a lot about what's going on in the early solar system because they also provided parent bodies of meteorites which falls on Earth, and you can do forensic studies of them. Here are the 4 main observational clues, and which we can construct theoretical models from. One is that clearly in the asteroid region there is a large amount of mass deficit, and it's by more than 2 orders of magnitude. And B, that in the asteroid region, you see collocations of both S-type and C-type asteroid. What are they? S-type are mostly made of silicate. They reflect a lot of light, and C-types are mostly made of very dark material, and they contain some sort of hydrated minerals. And so it's thought that the C-type asteroids form outside the snow line and the S-type form inside. But yet, when you look at them today, they're located at the same location. In addition to their elemental compositional difference, you actually see a lot of difference in their isotopic properties and material that's collected from S-type and C-type, objects, which are sort of known as non-chondritic or ordinary, non-carbonaceous ordinary chondrites versus chondrites, carbonaceous chondrites. It tells you that they may have formed from under a very different environment. So if they form under a different environment, they're located together today. It means they have migrated and they had a lot of mixing. And how do you make that mixing going? The other thing is when you look at their size distribution, and just like folks who study planetesimals and study grain evolution, it's not a single power law. There's a break, and both for the S-type and C-type. So these are the 4 clues, and given that clue, and what can you make of it? Well, first is from clue number 2 and 3. It tells you that number 1 is a severe depletion of some sort of a solid particle. Number 2 and 3, it tells you that they were born in a widely separated place, and they were mixed together after formation. And then the size dependent tells you maybe something about how these objects are formed. There are some implications on so-called pebble accretion and many other issues here. And then finally, by looking at their forensic timing of these decay lines, it tells you something about the chronology of the early solar system. So I only have 4 slides, and many of the details is completely hidden here. and just take these cartoon pictures. And first is that there are really two groups of models, and I'm going to advocate mine, but I have to badmouth somebody else's first. And there's a so-called Nice school, and the Nice school basically make the assumption that that how these objects S-type, C-type were formed is that they were separated by Jupiter, and the S-type was formed on the inside, and the C-type formed on the outside. And by looking at their isotopic differences, it tells you something about the sequence of when this thing happened. And then to get them mixed, so and they introduced the so-called Grand-Teck model, so you can have the Jupiter move in, migrate in, and then it starts to migrate out. And when it migrates in, it shuffles all of this S-type to this side. When it migrates out, it shuffles some C-type in. So you get left behind some system like this. The advantage of this model is that you can empty out this large region, so you can actually form low mass Mars. That was the original motivation, but there is some interpretation of this kind to tell you you can also explain the composition. One of the problems is that if you do this, okay, as you move in and out like this, first of all, there's theoretically it requires extremely fine tuning to get this kind of migration going. So as a theorist, I find it difficult to accept something that has only 1% probability. But there's only one solar system, so you don't need to worry about that. However, if you move this in and out, and that Jupiter has to move into the S-type region first, once, and then it has to go through it again, and to shuffle something in, so you can get this mixing. So that means around Jupiter, it should actually pick up some stuff on the Trojan resonance, one-to-one resonance, and there should be some S-type asteroids. Nothing is found there. A more natural way, of course, is the way that I would refer to as in-situ formation, that things didn't move that much, but it moved a little bit. And this picture is that the snow line was well inside where Jupiter was, and that you had S-type form inside and C-type here. And then Jupiter during its formative years, as it grows, it perturbs the gravitational field in the nearby region. As a result, it destabilized this orbit. It pushed a lot of the C-type into the S-type region, and then you can get mixing here. But there is a problem with that, is that when you do this, there's not enough depletion. So to get the depletion going, you go to the next stage. The next stage is that during the growth, after the growth of Jupiter, and there's still nebula around, the nebula will introduce small amount of gravitational field to the potential, and this will cause Jupiter to precess. And that precession will have a frequency where that frequency matches with the frequency of the precession that its secular effect perturbs the asteroid, and there is a secular resonance. At the location of the secular resonance, you can have eccentricity gets very excited, and this as a result of this eccentricity excitation, and you may have damping because these asteroids would interact with the gas. The small asteroids, they experience hydrodynamic drag, and so they're very effective in damping down their eccentricity. As a result, they will migrate inwards. And the large planetesimals, very large ones, they interact with the disk via tidal effect, and they're very effective. So they will also be emptied out. So as a result, you actually have a preferred size distribution. So you can actually produce this type of size distribution for both S-type and C-type, and then most of these planetesimals would tend to move inwards because secular effect takes away angular momentum, whereas the circularization takes away its energy. So as a result, their semi-major axis will evolve, and you can get the thorough depletion of the asteroid region with the enhancement of this region to form the inner solar system, and that could actually give rise to the chronology that is consistent with what asteroids are telling you. And this effect can have many other implications. I'm just going to highlight two. And one implication is during this dynamical evolution process, you can expect giant impacts. And here is a giant impact between Jupiter and a planetesimal as a result of core accretion. Jupiter had a major core, and then this dynamical instability can lead to competing embryos to collide with Jupiter. As a result, you destroy that core, and to account for the so-called diluted core of Jupiter. And the second implication for many colleagues here are the debris disks, where you tend to find, maybe sometimes you find disks with very small inner disks and separated by a factor of 10, some outer disks, such as in Fomalhaut and Vega. And one way to do it is through this type of secular resonance, and sweeping secular resonance, you can open up a big gap. Thank you. Yes, but if you actually enter into the envelope, there's already quite a bit of drag that associated with it. We calculate the collision probability, and that collision probability is reasonable, a few percent at that rate. And and then the other thing you need to calculate is afterwards whether the disintegrated core will settle back in or not. And it's a very subtle issue, and I would love to chat with anybody else further along.
Questions for that? Looks like everything was clear and convincing.
Thank you. I have a bridge to sell. Okay. Let me take here. Sure. How do I do this? There you go. Yeah.
Okay, so let me just motivate this idea of protoplanetary disk demographics by talking about exoplanet demographics. So the basic idea here is that, now that we sort of know of thousands of exoplanet candidates, people have started to do a lot of work on their demographic properties. There's a variety of ways of looking at this. I like this plot from John Johnson's PASP review in 2010, sort of building on his thesis work, that basically shows for giant planets like Jupiter, there's a pretty strong relationship between the host metallicity and the host mass and the abundance of planets. Right? But there's many different avenues to look at the demographics of exoplanets. So the field of planet formation has primarily been theoretical, and the basic theoretical path was sort of pioneered by the guy who just spoke, Doug Lin, and his colleagues, where basically what you do is you sort of are aiming to reproduce the demographic properties of the exoplanet population. And in order to do that, you build a model of increasing complexity of the physics that takes you from their birthplaces, protoplanetary disks. You take some initial properties of protoplanetary disks, those demographic properties, and you try and forward evolve the systems, many different systems in a statistical sense, and reproduce the exoplanet population. So a lot of the stuff that we do here on protoplanetary disks is trying to give them inputs to the start of their code. I'm really talking about initial conditions in this context in some sense. And later this afternoon, I'll talk about some more of the sort of details that we can influence. This is the real question, right? So the field has been primarily theoretical. The disk side of the field has been primarily theoretical because people didn't really know that there were disks until 20 years ago or so. But there are some observations that can be pretty useful for this context. And I just want to motivate that. If you know me, you know I primarily work in the millimeter. And I'm going to argue that the reason that you work in the millimeter is it's sort of the more physically informative in the context of these planet formation models. So this is just a plot from a review I did a few years ago where we're looking at basically where emission at different frequencies, this is thermal continuum from dust grains in these disks, where the emission at different wavelengths is coming from. So this is the height, Z over R in the disk, so higher up in the atmosphere, down towards the midplane, and this is radius. And these are sort of the cumulative distribution of the total flux from these different wavelengths, right? So I've picked sort of natural wavelengths. I mean, I think you can gauge from this where I'm going is that basically if you're optically thick in the infrared, right, you're tracing small dust particles way up in the disk atmosphere. You're not actually seeing anything relevant to planet formation, which is happening in the midplane. The millimeter continuum is mostly optically thin, and so you're effectively tracing the mass distribution. So the nice thing about the infrared, which is where the field sort of started, is that it's really bright, and it's pretty straightforward to do photometry, and you either see an infrared excess from a disk above the stellar photosphere or you don't. So you have a binary metric, basically, and you could use that binary metric at looking at stars of different ages and get some idea about the evolution time scale of these disks. And if you look at this plot, you're seeing sort of, usually done at sort of 3 microns. So you could basically say the time scale at which the disk inside of an AU is dissipating, right? So until sort of 10 years ago, that was the demographic property that you had, and the rest of it relied on sort of theoretical presumptions about protoplanetary disks, mostly based on models of our solar system, right? So what we've done over the years is basically try and measure the first step, right? Try and measure photometry in the millimeter continuum. I should say that like the field developed in such a strange way. It was sort of like there were incredibly detailed theoretical models even in the 70s. And we had basically no observational information. So when the observations started building in, people immediately went into detailed interpretations of the observations. It's kind of like a complete opposite of how extragalactic work evolved, where you first did luminosity functions and Sirsic fitting and so on and so forth, and then you built dynamical theories either simultaneously or afterwards. So my perspective has sort of changed, and I like to take a big step back and say, let's look at the luminosity distributions. Now, you should keep in mind that the millimeter luminosity distribution is roughly comparable to the dust mass as well, but I'm going to talk about luminosities. So this is sort of a useful plot in the context of John's plot that I just showed, where I'm plotting the millimeter luminosity, sort of disk mass, as a function of the host mass. And you can see here that there is a correlation between the two. You can see that in the cumulative distributions where I've broken it down by spectral type as well. So there's a pretty strong correlation, but there's a huge amount of dispersion as well. I'll explain if you do some corrections. Now, the end goal is to actually look at that as a function of, look at the luminosity distribution as a function of time. So I've just sort of split into 2 categories here. The gray points are all the points I just showed you before, and the purple points are from older hosts. And basically, it's a little bit hard to tell here because it's a somewhat subtle effect, but these tend to be over here instead of over here. And the difference is basically sort of a factor of 5 over a time scale of a factor of 5, right? So the luminosities are decreasing over time, and how you interpret that in terms of the mass evolution is a little up in the air, but feel free to ask me about it. Surprisingly, in the last few years, there's been sort of enough data taken that this other correlation sort of popped out, and that is the millimeter luminosity, so the dust mass, scales with the accretion rate of gas onto the star. Now, this is roughly linear correlation. That is interesting and could make sense in the context of basically linking the accretion rate to the gas masses. So this is all photometry, right? There's sort of no resolved information, but you can learn a lot to connect to these populations, planet population synthesis models, right? So let's just assume for the moment that the millimeter luminosity scales with the dust mass. Then we know that the dust mass scales roughly with the mass of the host, scales roughly inversely with the age of the host, and scales roughly linearly with the accretion rate out of the host. But if you look at those plots, there is a huge amount of scatter, and there's a lot of different ways to produce that scatter, but you expect that some of that information in the scatter is tied to the spatial distribution of the disk material, right? That's actually what the population synthesis models want, is a density distribution of the disk material. So this is where it becomes harder and harder to do demographic studies, because actually spatially resolving a large population of disks is very time consuming. So one thing that you can do is just cut it down to a simple metric of the spatial distribution, and that's sizes. And surprisingly, there wasn't really a survey of disk sizes until last year, when my former student Anjali Tripathi did the first one. So basically what we did is we observed now in 2 papers, right? We observed 100 or so disks, spatially resolved them. We just do some simple models. These are Nuker profiles. These are the extragalactic profiles people use for elliptical galaxies, but they're just some simple parametric form. We fit the visibility data. The key point is that basically you can construct a sort of model-independent size metric, and that's basically like a half-light radius, right? So that's what we're talking about with size, half-light radius of the continuum at this frequency. And the thing that's sort of surprising, I don't know whether to be surprised by this or not, to be honest, but at first it was surprising, is that there's an incredibly tight correlation between the millimeter luminosity or dust mass and the size of that millimeter emission. It's not so surprising that there's a correlation. What is surprising is the shape, because it basically says the continuum emission psi, or continuum emission area projected on the sky scales with the luminosity of the source. And that's not what you'd expect if the emission was either optically thick or optically thin, because in both cases the intensity profile decreases with radius. So that's interesting. What we've done now is sort of try to fold the two things together, right? Link the sizes to the host properties, right? So this is the continuum luminosity, and this is the host luminosity, mass, and again, a continuum luminosity. I've cut off the top thing because, well, maybe some of you care about the mass luminosity relation for young stars, but I don't. So you have actually all these correlations that they're all actually directly related to one another. And that actually opens up this picture to be a little more complicated, because it basically tells you that everything's dictated by the spatial distribution of the solids in these disks. Right, so we made some sort of cheap toy models of these scenarios to try and explain, with a minimal number of assumptions, the behavior of these trends and the scatter around them, to see sort of what is dominating the scatter as well. These are the results. These are sort of like probability density maps. And this is the takeaway. It's basically just that the spatial distribution of solids matter, which I said, but you can actually reproduce all those relationships with either optically thick or thin emission. And so if the optical depths are, this is sort of a cheat, if optical depths are actually high, assume all the emission is optically thick, you need to actually remove some parts of the disk to get a filling factor of about 1/3. And then you can actually do this. The only thing you need to assume is that the disk sizes scale roughly sublinearly with the mass of the host. And if you have the standard optical depths are low, it implies that you have a common density profile. The only thing that matters is where the material stops, right? And again, you need the size to be scaling roughly linearly with the host mass. I don't actually know what that means, I should tell you. But it's an interesting possibility that the optical depths are actually high if you remove a lot of material, especially in the inner part of the disk. And if you want to know sort of why that's interesting, I'll tell you in a few hours why that might be the case. So thanks. Right. So that's an excellent question that I just explained to the referee of our paper, which I assume wasn't you, but that would be interesting. Right. So it is true that it's very difficult to populate down here because of optical depth effects. Right. Basically, it sort of depends on the host luminosity, but you would have an optical depth. Tau is large, cutting like this. It has a different slope, but this is not surprising. But we're sensitive all the way up to here. Like, we should see all those disks that are up there, and they do not exist. Well, so yeah, indeed, they're obviously less abundant because they don't exist. Right? But yeah, the question is, why don't you actually have low surface brightness big disks? Right? I don't have an answer for that because it's just still in the empirical phase, but that's sort of where it's going. You could, yes, you could. I mean, this is 100 disks, and it's hard to do a lot better. I think actually the more interesting direction is this is a frequency or wavelength dependent thing, right? So there's a lot of opportunity to actually go to a longer wavelength, right, where you would actually be picking up, does this trend persist? Because that tells you about the evolution of the solids. But yeah, it's true. If you went 100 times deeper and you still saw nothing, then that's really important. But, you should be on the Alm attack. If you think that's a good idea. Thanks.
Okay, so it's a great pleasure to present some work we have done last year and published it in Nature Astronomy on gender bias in astronomy. And a lot of people who know me, they came to me and asked me like, hey Sandro, why are you not talking about galaxies? Are they not interesting anymore? And of course, galaxies are still very interesting and close to my heart. But as Avi already mentioned before, the reason is that thanks to Nia and Anna, we had a very great journal club last semester on equity and inclusion here at the CFA, and it will take place again next semester. And one of the outcome of this is that we have now every month one of the talks will be on this topic. And of course, I want to thank here in particular Anna and Nia to organize this club, but also Avi, Charles, and the ITC to give us the opportunity to learn more about this, I think, very important topic, and also build a more inclusive environment for the future. So now, why did the three of us here, Nevin, Simon, and me, really look into this topic in the first hand? So what is the link between us? So we all did the PhD at ETH Zurich and graduated all together last year. And so this is what connected us, and basically the initial idea came from a very interesting talk given by Meg Urey back in 2014 at ETH, where she gave a talk on women in science, why so few. And what was really impressive was that she presented a lot of hard data on this topic, not just anecdotal evidence, but really hard data on this topic. And so we then thought that, it would be interesting to look into this as well, in particular looking into citation counts. But again, I want to stress here that we are not, experts in that field. So we took really this kind of project or idea more from a data point of view. So we really just thought we collect data and we look into this because we can play with data. That's what we learned through the last 3 years. And so let's look into this, what the data is telling us. Of course, other people have looked already into gender differences in astronomy. So there is this study, for example, by Davenport et al. 2014. They analyzed 225 AAS talks. So they looked into who is asking the questions in the audience. And so they found that the speakers and the audience are making maybe roughly 35% of all the people are females there, but only 25% of the questions that were asked were female. So there is, it seems that women are asking less questions. And they were interpreting this as kind of an age gradient because, older people, more senior people are asking usually more questions, and usually they are more males. Then there was also the important study by Wright et al. Who looked into HSD, Keck time, basically who gets the HST, the Hubble Space Telescope time, and here you can see as a function of cycles, the success rate of proposals. And you can see here the red bar is showing you the success rate for male PIs, and the green bar is showing you the success rate for female PIs. And you can see that the blue bar is always higher, throughout the years when you go back in time than the female ones. And so this shows you that women are less likely to get telescope time. Now, the interesting part of that story is that they also looked specifically in cycle 21 and looked into what is, the age distribution, or what is the year of the PhD. And so you can see when you go to the most recent PhDs, you can see that the male and the proposals that were approved, now this is unfortunately the absolute number, but it's the same for male and female PIs. But when you look into the, submitted proposals, the male are making the much larger contribution. And so actually, when you go to the youngest ages, or, the most recent PhDs, there actually women are more successful in getting telescope time. But, the large difference comes in because when you go to kind of, people who had their PhDs longer ago, there, this is really where the difference comes in. And so we were asking the question, okay, how does it look when we look into citation counts? And so what we were doing is, thanks for the ADS that is also hosted here, we just collected a lot of papers, in total of 200,000 papers that were published in astronomy, in Science, Nature, APJ, ANA, and MNRS from 1950 to 2015. And so we collected all this information back in 2016, and if the archive posting was also available, we also took that in order to estimate the length of the paper. Then a crucial part of the analysis was adding the information about the authors. So the first thing is, the country of origin, which we, took from the affiliation. Then what we did, we really mapped individual authors through time. This is not so trivial because there is not really an ID system. Now, one is implemented and it's coming up in the next few, it's hopefully used more in the next few years. But basically, we really had to go to the last names and match them with the first names and, do this in a very careful way, through time, basically. And then we looked into the seniority, and we defined it to be like, when the person has published his or her first author paper. And then we determined the gender based on the first names. Again, it's not very trivial because you have names like Andrea. So where I come from, and Andrea is a name for a man. Here it's more for a woman. And so, we assigned actually probabilities based on what we got out from different databases. But overall, the agreement between the databases is quite high. So the database is available. You can check your name and see whether we did quite well or not. It told us that we had a bit over 200,000 papers. We had really to clean because we wanted to have a kind of rather pure sample. We really want to have bijection, in the author lists. And so we were cleaning up the data and ended up with a, data set of 150,000 papers. And so this is, I'll show you a few, just properties of the sample, basically. So here you can see the number of papers as a function of the year where the, paper was published. You can see that it's increasing over the past few years. This very small dip in the recent years is just because we only included papers that have at least one citation. And then you can see the fraction here of, female papers. I call female papers just as a short term for, papers that have a first author to be a woman in our analysis. And you can see that, this fraction increased from, a bit less than 10% to about 25% today. When we look into the average number of references of papers, we again split by male and females. You can see that the first authored, papers by females have more citations on average, and this is, significant basically at all years. Another thing to look into is the average seniority of the published papers, and you can see that, usually the papers that are authored by male on average have a higher seniority. And I think something also very interesting to highlight here is, the fraction of female papers split up by different journals. You can see here ANA, APJ, and MNRS, which makes, of course, the largest part of the publications. You can see that they are of the order of 25%. But when we go to Nature and Science, we can see that the fraction of first author female papers is clearly lower. And, we talk here only about 15%. And so there, it seems to be a difference there, which has been already highlighted by other studies, of course. So what is with citation counts? What I show you here is the ratio between male and female, number of citations, average citations, and you can see that it's always kind of above 1. So this means that we see of the order of 6% more citations for papers that have a male as a first author. Now again, this is not gender bias. This is just showing you a difference. And as we I tried to tell you with the HST analysis, the Hubble Space Telescope analysis. It can be that there is not a property hidden here. For example, the age. And so the question is really, how can you control the difference in the properties of the whole sample? And so the idea that we had is to train a random forest algorithm on the sample of papers written by men, and then use it on the sample of papers written by women. And then look at the predicted numbers to the numbers that, the citations the paper really has. And so what kind of properties did we train? So we tried to get as many properties as possible, and here are the key properties listed. So these are also all non-gender specific parameters. The seniority I mentioned before, the number of references in the paper. This traces rather well the length of the paper. The total number of authors. This kind of takes into account collaborations. Year of publication, journal of publication, field of study, and the geographical region of the first author's institution. And so now what we assumed is basically that men and women should receive the same number of citations for papers that have the same non-gender specific properties. So if you match a paper with these properties, men and women should get the same citations. And if there is a difference, we call this then gender bias. And so this is basically the main result. This shows you the measured over the predicted number of citations, for the women paper, and you can see that it's always, below 1. And so we measure actually gender bias of 10%. And so just as a summary here, so again we analyzed over 200,000 papers. 6% is the difference, but when we match basically the properties, we find that there is a bias of 10%. And so this means actually if there would be no bias, women should on average receive 4% more citations. And again, this is probably because when we look into the importance of the random forest algorithm, we see that number of references is a very crucial point, and it seems that women are writing usually longer papers with more references, and this seems to drive, basically if there would be no bias, a higher citation rate. Okay, thank you very much for your attention. It really depends how you fit the data and extrapolate, I think. You can see that, it seems to be, when you just ignore everything before 2000, it seems to be rather flat. I mean, if there is a lot of, the error bars are also larger. It's quite noisy kind of here in this region, I would say. It's getting better here, and so it seems to be rather steady at the moment. We haven't looked into that specifically, but we find a trend that for the whole sample, that if the seniority is higher, the citation count is higher.
But I guess I'm
yeah.
Like as a young woman myself, when I write papers, will people cite me less than older women?
Yes,
oh.
but we can. We can look into this. As I said, the data is public. There's actually quite a lot of stuff, ideas, what one can do, and more than welcome to look into this specific question. Yeah.
I'm not sure how relatively recent of a practice it is, but I see a lot of papers now where they are trying to anonymize the gender of the authors by using just first and middle initials. I guess I was wondering how much of an impact that had on the data collection. Like, was that a problem in more recent papers, having less data on genders in recent years?
Yes, I mean there's for sure a significant number. I don't think it's in recent years. Actually, in past, it was also done that many times just initials were used, and this is a major problem in our analysis. We try to look into this in the sense that when we are not catching certain people at all. I mean, if there would be a bias in who is just using initials, this could lead, of course, to a bias in our analysis. We also were thinking a lot about, if people change their names, for example, if somebody marries and changes his or her name, mostly hers, then we are basically assigning, wrong seniorities to the people. But actually, this works in favor of our analysis in the sense that this would just be then a lower limit, basically, because we would just underestimate the ages. And so if people decide to change, going from being, whenever they mention once the full name, and then they change, I'm just using initials, then they will be caught in our analysis, because we really did, we used all the information that was there if it was bijective. So if there is, a Takela and the S once, and then one Sandro, and then just S forever, we will catch the Sandro and we'll assign it to all the Takela S, basically. HSD.
Just by without the name? Anonymous. Anonymous. Yeah. So these are practical attempts to solve the problem.
Yes.
Any other comments or questions? If not, thank you all for coming.